This video is for Calculus BC, section 9.8. In section 9.7, we have been learning how to write Taylor polynomials, and then we use those Taylor polynomials to approximate a function. Sometimes it was e to the x cosine of x, ln of x, some other transcendental function. We looked at a couple of those like very fundamental type polynomials. What we're going to be doing in 9.8 is we're going to be considering the idea that if we continued those polynomials, in other words, like we didn't stop the pattern after the third degree or the fourth or fifth degree, but if we just kept on going with those polynomials to where we have an infinite number of terms, we would have something a little bit more unique. We'd have a situation where the function that we're trying to approximate could be exactly represented for certain values of x, and we would call these series a power series. And I want you to think about this. In the previous section, we looked at the Lagrange error bound, and in a couple sections prior to that, we looked at the alternating series error bound. If you think about it, the more terms you have in any polynomial approximation, the lower the error, right? You think about that alternating series error bound is based on the value of the next term, the first omitted term. And so the further along you go in that polynomial, those terms just get smaller and smaller. And really the same is true of Lagrange error bound as well. It's just not quite as dramatic, but we still get, those terms are decreasing as you keep adding terms onto the end. So the more terms you add, the lower the error. So if you think of this in terms of, well, if the number of terms approached infinity, then wouldn't the error approach 0? So not all of the power series that we're going to look at are going to converge or match the original function for all values of x. Some of them will, some of them won't. And so we're going to be looking at here in section 9.8 a little bit is how to decide where these power series actually converge, like for what values of x these power series actually do converge, and maybe there are going to be some areas that the power series does not converge. And so if you look here at kind of the start for a power series centered at 0, power series centered at c, hopefully those look very familiar to you. Those are simply kind of a recounting of a Maclaurin type series or a Taylor type series, and hopefully we've done a pretty good amount of practicing with those, and you remember what those are. But let's take a look at that next section down below, where we start to talk about where these series, for what x values these series actually converge or not. So there are three possibilities. So here's number one. It's possible that the series, and we're talking now about an infinite series, it's possible the series might only converge at its centering point. It's also possible that the series might converge for all values of x. And then there's kind of a middle possibility where there's kind of a limited radius where the series will converge for certain values of x, but not for others. A broader interval of convergence than just c, but still limited in that it's not for all values of x. And we're going to look at how to figure this out. So we call the number r, whatever that is, we call that the radius of convergence. Just tells us the reach, if you will, of the convergence, how far to the how far on the x scale this convergence actually goes. And we're also going to be looking at the interval of convergence. One note here, I guess, may be worth mentioning. If the series does converge for all x, then we'd say that radius is infinite. And if the series converges only at c, then that radius of convergence is 0. So then, in order to figure out what the radius of convergence is, and then by extension the interval of convergence, we're going to use the ratio test. So there's just a review of the ratio test. It's the same ratio test as what we talked about back in section, I think it was 9.6. So take a minute and review a little bit, but nothing has changed there. We're going to be looking for convergence, though, so I guess I should mention this, that we're only really going to concern ourselves with this first piece. We're trying to find the interval of convergence or the radius of convergence, so we won't really look at the other parts there, at least as frequently. Okay, so let's go ahead and take a look at a few examples. Example number 1 comes up first. So this just says find the radius of convergence of this series right here. So I'm going to start off with the ratio test. I'm going to write it like this. Limit as n goes to infinity, and we always put the absolute values in there. Of course, the absolute values take this alternating element out of the picture. And so all I'm really concerned about here is the n plus 1th term, so that would be x to the 2n plus 2, if I distribute that 2, over 2n plus 2 factorial times the reciprocal of the previous term. So that would just be 2n factorial over x to the 2n. And in order for this to converge, we want to set this less than 1. Okay, like before, we're going to do a little bit of manipulation with the pieces inside the absolute values. So here we go. If I look at my x's, x to the 2n plus 2 and x to the 2n, if I am dividing my bases, I subtract my exponents. And so that would be x squared, right there. And then the factorials. If you remember from before, the factorial 2n plus 2 factorial would look like something like this. It would be 2n plus 2 times 2n plus 1 times 2n factorial. I'm trying to squeeze that in there. Hopefully you can read that. And so hopefully you can see that if we did think about it like that, this 2n factorial would cancel with this 2n factorial, leaving me with a denominator of 2n plus 2, 2n plus 1. And again, I'm looking to have this be less than 1. Now I'm going to try to apply my limit as n goes to infinity. So keep in mind that x is just standing for some kind of an input, right? Like when we try to approximate what's going on at 1 or 0.1 or, who knows what it could be. But x is just going to be some number, and then of course squared. When you think about this limit now, limit as n goes to infinity, you're going to end up with the top, the x squared is just going to be some number squared. The denominator is going to be increasing without bound. Now think about what that means. That means the whole left side is going to 0. So 0 is less than 1. Okay, so then we ask ourselves, what does this mean as far as a radius of convergence? Well, for what values of x do we get this relationship? In fact, if you think about it, this relationship right here doesn't depend on x at all, right? 0 will always be less than 1. So this relationship does not depend on x at all, and so I would say that our radius of convergence is infinity. It doesn't really matter what you plug in for x, you're going to get a convergence. I don't know if you guys noticed this or not, but this original power series up here, this is the series for a function that we've already talked about. Notice how the exponents are even, the factorials are even. This is actually a power series for cosine of x. And if you think back on the calculator activity we did with this, as we continued to add terms, that radius of convergence continued to grow and get bigger and bigger. Hopefully you remember that how that worked graphically. We see it now here with this ratio test about how the radius of convergence is infinite. Okay, next one we're going to look at here is number 2. So number 2, as always, you guys have seen one of these done, so if you're watching the video here, maybe it'd be a good idea to pause the video and try this one on your own. Certainly a good idea, and obviously you can play the video and see how you did. Okay, so radius of convergence, we're going to set up that same ratio test. So limit as n goes to infinity, and then absolute value of the n plus 1 term, so it'd be x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. That whole thing is supposed to be less than 1. Okay, so like before, we're going to do a little bit of that work with the exponents and the factorials. So I think my next step would be the limit as n goes to infinity. I'm going to subtract my exponents on the x's, giving me just x to the first. And then with my factorials, I'll just end up with n plus 1 in the denominator. So let's stop for a second here and analyze this limit. Really a pretty similar limit to what we just had in the perspective of the top is going to be held to essentially just numbers, right? You're going to be plugging in some real number for x, but the denominator, n plus 1, because n is headed to infinity, of course infinity plus 1 is just infinity, so the denominator is increasing without bound, and so we have a really similar situation as before, where the top is going to be just some number. Actually, that's not very good. Let me write towards infinity. The top is just being held, as some number, and the denominator is increasing towards infinity. That's a recipe for 0, right? So 0 is less than 1. We've got the same kind of relationship where that limit doesn't depend on x at all. And so since 0 will always be less than 1, and it doesn't depend on x for this relationship, there are no x values that don't work. In other words, they would all work. So like before, I would say that my radius of convergence is infinity. And again, I'd encourage you guys to think about this. X to the n over n factorial, that actually is a pretty familiar series. Can you think of what that power series represents? Hopefully you're recalling that's actually the power series for e to the x. E to the x does have a power series that converges for all real numbers. Therefore, the radius would be infinite. Okay, let's take a look at number 3. All right, number 3 here. Let's set up that hopefully familiar ratio test. It looks like this. Limit as n goes to infinity of the n plus 1th term. So if I plug an n plus 1 in for n, I'm going to get x to the 2 parentheses n plus 1 over 2 parentheses n plus 1 factorial. We'll sort that out in a second, times the reciprocal of the first term, of the previous term. So that would just be 2n plus 1 factorial over x to the 2n plus 1. That's less than 1. Okay, so if we want to do that little bit of arithmetic there, in the first factor, we're going to get x to the 2n plus 3 and 2n plus 3 factorial times, of course the other factor doesn't change, x to the 2n plus 1, and there we go. Okay, so like before, we're going to do a little bit of work with the factorials and the x's. Let me remind you of what the factorials are doing here. This 2n plus 3 factorial is really 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So that means that this 2n plus 1 factorial and this 2n plus 1 factorial will cancel. If I do a little bit of work with the exponents on the x's, subtracting, namely, I get limit as n goes to infinity of x squared over, and I'm just left with 2n plus 3 times 2n plus 2 in the denominator. I hope this is starting to look familiar to you. Do you see how the numerator, once again, is going to be held to essentially some constant, right? X is going to be some number that gets plugged in for x. We square it, but bottom line is going to be some constant. But the denominator is increasing towards 0 or increasing towards infinity because of that limit, and so the value of the fraction overall is headed towards 0. So we get 0 is less than 1 again. So like before, the radius of convergence does not depend on x at all. That left side of this inequality is going to be 0 no matter what x is. And so that means our radius of convergence is infinity. So you might be tempted to think that, oh, hey, look, we've done 3 problems, and so far all of the radius of convergence has been infinity, so they must all be like this. Well, that's not true. So I think we'll do one more example in this video. Maybe we'll split 9.8 up into 2 videos. We'll do one more example in this video to show you that that's not always the case. To help us do that, we're going to move into this next little subsection where we're going to be finding interval of convergence. So this is really similar to what we just did. We're just going to be taking it one step further. In order to take it that one step further, we have to consider what's happening at the endpoints of that radius. So here we go. Number 4 says find the interval of convergence, and there is our power series x to the n over n. So set up the familiar ratio test. Limit as n goes to infinity of. We're going to set up our n plus 1th term, so it'd be x to the n plus 1 over n plus 1 times the reciprocal of the previous, or the first term. So n over x to the n, and we want this ratio test to be less than 1. Again, very similar process to what we've been doing. Limit as n goes to infinity. We're going to subtract the exponent on the x's, so we get x to the first. But then we don't really get a cancellation with the n's. I'm going to rewrite it just a little bit differently. I'm going to write it as n over n plus 1. But we don't get that. There's no factorials for us to cancel like before, and so we don't get that quite as familiar situation. So let's keep in mind that this limit as n goes to infinity only applies to things with n's. So it only applies there. It doesn't apply to the x. So let's think about what happens here. As I do n going to infinity, what's the limit as n goes to infinity of n over n plus 1? You could use L'Hopital's rule. You could use the old pre-calculus trick. You could use the dividing by the degree of the denominators trick. There's 3 ways at least you could do this. The bottom line is that limit as n goes to infinity of n over n plus 1 is just 1. So what I'm going to get here is the absolute value of x times 1, or how about just x, is less than 1. All right, so for the very first time, our radius of convergence depends on x. So if you think about it, if x is 5, 5 is not less than 1. So that doesn't work. If x is negative 3, the absolute value of negative 3 is 3, and that's not less than 1 either. Think about what numbers work here. We don't have to just be those positive and negative small fractions, between or around 0, right? Between negative 1 and 1. So for the first time, if we were just going with a radius of convergence, we would say the radius of convergence is 1. Right? We can only go up to positive 1 or down to negative 1. If we go outside of that interval, then we're going to get a false statement. Okay, so we're not just going with radius of convergence here, we're going with interval of convergence. So let's talk about how this works. This will take you back a little bit to some your days in algebra perhaps. When you've got the absolute value of x is less than 1, we have to consider both cases. First case is this: x is less than 1. We just drop the absolute values. The other case is this: x is greater than negative 1. So I'm going to write this a little bit differently. I'm going to tentatively, and tentatively just means I might have to make a little change here at the end. I'm going to tentatively write my interval of convergence as this: I want all numbers that are bigger than negative 1 and less than 1. As I mentioned before, I'm going to have to test the endpoints here, and so I might be putting some more equal to's on there. I might be closing the interval a little bit. We shall see. And here's how we do this. We're going to test our interval out. I'll switch to a different color so you can kind of see this a little bit differently. I'm going to test out my endpoint. So I'm going to write it like this. For x equals negative 1, I'm going to test that first endpoint. I get sigma from 1 to infinity of negative 1 to the n over n. This is where those old convergence and divergence rules are going to really help you. By any chance, do you recognize what kind of a series that is? It is my hope that we would see that this series right here converges. And the reason that it converges is that that is an alternating harmonic series. It's an alternating harmonic, and the alternating harmonic always converges. And that's really all you have to write. What I would do then is I'd come down here and I'd say, well, for my left endpoint, I get a convergence. And so I'm going to put or equal to on that. I got to also think of my other endpoint. So for x equals 1, that's my other endpoint, I get sigma from 1 to infinity of positive 1 to the n over n. That series actually diverges. And the reason that I would list is that that is a harmonic series, and harmonic series always diverge. So I would not put the or equal to on that right endpoint. So this would be my final answer for my interval of convergence. Negative 1 is less than or equal to x, which is less than 1. You can still see that radius of convergence, my centering point being 0. I can go all the way out to 1, but not including 1. I can go all the way down to negative 1, including negative 1. Okay, so I wanted to make sure we had that in there just so you realize that not every single radius of convergence was infinity. Check out part B of 9.8 in order to see the rest of the examples here.